We are team 22085, and our senior design project consisted of us developing a proton exchange polynorbornyl membrane for fuel cell application. Our mentor was Dr. Dominic Gervasio. My name is Elliot.
I'm Ahmed.
I'm Yusuf.
I'm Aaron.
And we're all chemical engineering majors.
So the goal of this design project is to chemically modify an anion exchange membrane to perform as a proton exchange membrane in an attempt to realize a more robust and efficient solid state electrolyte for use inside of a fuel cell and other electrochemical devices. To understand why we chose to do this project, some background is needed. The problem this design project tries to address is that the current PEMs on market, like Nafion produced by DuPont, can only operate at temperatures below 80 degrees Celsius because their membrane requires a certain level of hydration to ionize the acid responsible for conduction, which directly translates to bulkier external management systems to maintain its operation. So if fuel cell technology is going to remain competitive in a clean energy market, we need to do better. The polymer we chose, first synthesized by Polycoal of Georgia Tech, offered us a stable platform to use in high temperatures. Based on the recommendations from our mentor and from literature, through the chemical addition of ammonium phosphate pendant groups, these immobilized salts, which are bound through covalent and electrostatic forces, are insoluble in water and will not leach in the presence of it. This membrane, combined with these modifications, offered us the desirable properties we determined necessary to overcome the current challenges to PEMs.
All right, so here's what our experimental outline looks like. We prepared the amine phosphate first as electrolytes. Remove the water from the amine phosphates using a rotary evaporator. Determine which electrolyte has the highest conductivity. Then prepare and run a liquid phosphoric acid fuel cell to use as a reference. And then prepare and run those amine phosphate fuel cells and analyze their performance. Our testing protocols for determining conductivity consisted of utilizing a YSI conductance meter to determine the conductance of the amine phosphates. Then using theoretical relationships, we determine conductivities. That initial step is just to give us a reference on which amine will perform as the better electrolyte. Highest conductivity means better performance. The fuel cell has four major components: the Teflon block, electrodes, current collectors, and a steel housing. The fuel cell performance was tested by utilizing a Power Suite software to generate voltage versus current density plots. From those current versus density plots, the performance is going to be analyzed.
All right, so here's our experimental setup. We've got our oxygen and hydrogen tanks on each side, each are 20 feet apart. And over here we have our working station where we work on assembling the fuel cell. And as you can see here, we've got a phosphoric acid right here with a magnetic stir bar just to make sure that it's in good condition. Here's our oven with a thermocouple at the very top to let us know what temperature the oven is at. As you can see from the inside, we've got our fuel cell hooked up. We've got our in and out on each side. This side, of course, we have the oxygen flowing in, and on that side, we've got the hydrogen flowing in. As we move out of the fuel cell, as you can see here, we've got some bubbling. This just lets us know that there's no leak in the system and that we're actually getting gas flowing out of the system. On each side, we've got flow meters, rotometers actually, that control the flow of the gases. And right here, we've got our computer and our laptop. Basically, this is what lets us analyze data and take measurements. As you can see here, this is one of the runs that we made. We got our potential versus current density and potential versus current linearized graph. Basically, this is what we'll be using to analyze our data.
All right, so these are our amine phosphate electrolytes. Each one, we started off with phosphoric acid and added the respective amine. From there, we put it in the roto evaporator and pulled off as much water as we could. Then we took conductance readings, and from those readings, we were able to determine which electrolyte we would like to experiment with inside the liquid fuel cell.
All right, so when taking the conductivity readings for each of our solutions, here are our results. Like Ahmed had said, we had used conductance meters to measure the conductance of each of our compounds, and using theoretical equations, we're able to get that into resistance, and eventually into conductivity readings. We knew phosphoric acid would have the highest conductivity, and we were looking for an amine compound that would get closest to this conductivity. And in this case was methylamine. This means we could use methylamine as our amine going forward in our industrial process. And when we took power and current, as well as voltage and current curves, this is what we got when testing phosphoric acid. This is the trend that we expected and we're looking for, and we will replicate these exact curves when we finish in the lab. We're currently replicating these curves using methylamine phosphate solution, and that's what those are the graphs we're looking to replicate right now.
Okay, so for our industrial process, we're doing a roll-to-roll process. We're rolling the membranes and we're making them go through 4 paths. So the first path is the amine path. So it's going to go under an SN2 reaction to aminize the membrane. After that path, it's going to go through a heater to dry the membrane. Then after that, it's going to go through another path, a sodium hydroxide path, to prepare it to react with the phosphoric acid. After that, it's going to go through a third bath, which is the phosphoric acid bath. And then we're going to rinse it with a water bath. And then at the end, we're going to dry the membrane again. All right, so for our utility table, we're producing around 33,000 50 centimeters by 50 centimeters membrane each year. And then we're looking at electricity consumption of 36,000 kilowatts hours per year, and then around 1.5 million of meter cube of water.
Right, and throughout this whole project, we were met with lots of ups and downs. Some of the highlights that we experienced throughout this process has been we were met with great success when preparing all the amine phosphate electrolytes for the fuel cell. We were also able to use these amine phosphate electrolytes to select the one that we would use industrially. And all of these, even though there was setbacks along the way, we did learn a lot about collaborating with team members, project management, how to adapt to any unforeseen challenges in whatever situation we're in, and what makes a good design of experiment. And although there were highlights, there was also setbacks. We had to change labs throughout this semester. We had to remachine our fuel cell because it had leaks and impurities. And as well, we had trouble ordering our chemical supplies. And finally, it was just difficult to run these experiments with the fuel cell to get good data and data that we could use. But overall, it was a great experience, and here are our references.
We are team 22085.
This concludes our senior design presentation.
We appreciate you taking the time to watch our video.
Please vote for us.
Thank you.
Thank you.